I'd like to introduce you to Gustavo Silva for his wonderful talk today.
Okay, thank you. Thanks. Thanks for having me. It's my first time here in Australia. And well, I would like to start by saying thanks to the organizers for the opportunity to be here. And well, I just want to have an idea of the people in the audience. So how many of you are kernel developers? Okay, well, that's mostly half. and apart from them, the rest of the audience, how many of you are professional C developers? Okay, well, awesome. Okay, well, another question. How many of you know what fake flexible arrays are? 2 people. Okay, that's great. That's amazing. Okay, let's get started. Well, my name is Gustavo Silva. This work is supported, my work in the kernel community is supported by the Linux Foundation and the Alpha Omega project. So a couple of words about me. I have a background in embedded systems, and I've been doing upstream kernel development for 8 years now, and mostly focused on security. And I collaborate with the Kernel Self-Protection Project, which is part of the Google open source security team. It's just the Linux kernel division. Okay, this is the agenda for today. We are going to, sorry? Okay, so why? I guess. Okay, awesome. Okay. Okay, great. So, but can you hear me well, right? Awesome. So this is the agenda for today. We're going to start by saying a couple of words about arrays in the C language. We're going to start with the very, very basics, and we're going to move up to bleeding edge upstream kernel hardening. And well, let's start with this. This is probably the most simple declaration of an array in the C language. So we have happy array, which is an array of a concrete size. And well, but arrays are a building block in software development, right? So they are quite useful. We can iterate over them. We can read, write at once to them. And well, happy array is going to remain happy as long as we access this array through its valid indexes, which in this case is going to be from index 0 all the way up to 9. However, the C language doesn't enforce boundaries, so that is up to the developer to make sure that any access to the arrays are going to be within the boundaries. Otherwise, well, we are going to land into what I like to call the land of possibilities, which is undefined behavior. Okay, this is an example of a miserable array, just for completeness. Trailing arrays. Okay. A trailing array is merely an array that is going to be at the end of a structure. So here we have an example of struct trailing with a trailing array. Now, sometimes we need to use flexible arrays. Well, sometimes we need to use trailing arrays as variable length objects in the kernel. So that is an object that is going to live at the end of a structure in a runtime. We are going to be able to determine its total size. And this is an example of a flexible structure. A flexible structure is merely a structure that contains a flexible array at the end, which is, well, a trailing array as a variable length object. Currently, in the kernel, well, this is a bit of history. We're running into a lot of ambiguous declarations of this type of objects. We have basically 2 different groups of these declarations. One group that we call fake flexible arrays. So in this category, we have 1-element arrays and 0-length arrays. Here we have an example of those arrays. A 1-element array, well, it's merely an array that's going to be defined at the end of the structure with just 1 element. In a 0-length array, well, its size is going to be 0, right? Now, we have another way to declare this type of objects, which is a true flexible array. A true flexible array is a C99 flexible array member. So this is basically an array declaration with empty square brackets, right? there are some problems. Well, there used to be some problems in the kernel with these declarations, because, well, we had different ways to declare these objects. So that got us into some trouble. Here, I'm going to go through some of the issues with one-element arrays. So let's say that they are prone to off-by-one problems. So in this case, we have the declaration of a fake flex1 structure. And at the bottom, you can see how people usually allocate size for the whole thing. So in this case, count is going to be the variable that is going to contain the total number of elements for our array at runtime. However, if you notice, there is a subtraction. We are subtracting 1 from count because the size of the one element is already considered when we apply size of to star p. So developers, when developers use these types of objects, they need to be aware at all times that they are using a structure that is containing that extra size for the array. So that's problematic because whatever servo calculation or computation you want to do with the size of the structure, you always going to need to subtract the size of that one element. And well, this we've been currently trying to enable array bounds in the kernel. We've been trying to enable this option for a couple of years now. And we have run into a lot of false positives with one-element arrays. So in this case, well, the issue is that when we enable this option, this array, fake flex array, its only valid index is going to be 0. But at runtime, this array is being used as a flexible array member or as a variable length object. So developers are going to try to access this array through an index greater than 0. So that's going to be an issue. That's a bug. And well, we've been fixing a lot of this in the kernel. And if you happen to run into this problem, that's the warning that you are going to see. Okay, now, what is the issue with zero-length arrays? They are not part of the C standard. They don't contribute to the size of the containing structure. However, they are still a little bit buggy. Sometimes people apply the size of operator to this type of array, and well, the result of this operation is going to be 0. The thing is that sometimes we have found that they apply this operation to multiplications. So probably they were confused, and well, that's an issue, and we have fixed some of those. And again, at the bottom is an example of how people used to allocate the size for the containing structure together with the items in the fake flexible array. As you may notice, now count, the subtraction is gone because we don't need to subtract anything. And well, usually this is actually the recommended way to calculate the size for the allocation. We have the struct size helper, so just for you to know. Okay, well, let's see what size of, if we apply size of to one element arrays, what is the result? If we apply size of to one element arrays, we are going to get the size of that one element. If we apply size of to a zero-length array, of course, we are going to get 0 because, well, it's basically a size 0. In the case of a flexible array member is an object of incomplete type. So let's remember that the type of the object, part of the type of the object of an object in the C language is its size. So in the case of a flexible array member, it lacks a size, so size of, that's basically a build error. And well, that's another source of issues in the kernel. So having these different ways to declare a variable length object forces us to be aware of these type of issues, right? Okay, so well, in this case, ambiguity is the enemy in this case. We need to remove that ambiguity from the kernel. And well, we are going to run now into some of the, we are going to see some of the issues I have found while trying to address this problem in the kernel. In this case, while I was auditing some piece of code, I found this structure, and this is the commit that introduced the bug. So the bug here is that we had originally a zero-length array that at runtime is being used as a variable length object. So people here added a new member after this zero-length array. So at runtime, this is going to be undefined behavior. You did that? Okay, compilers are not able to detect these sorts of issues. So, well, what I did was, well, I fixed it by transforming this zero-length array into a flexible array member. So this is the fix. This basically was the kickoff for flexible array transformations in the kernel. And flexible array transformations is the effort to eliminate that ambiguity from the kernel. That ambiguity of having multiple different ways of declaring variable length objects and being aware of subtracting one from the one elements and being aware of all the different results that we are going to get when we apply size of to these different variants of declaring this type of objects. Okay, so, well, this was the kickoff. This bug, it was an 8-year-old bug. So, well, that was fixed in 2019. Another issue I ran into is this. In this case, we have a structure that contains an array of a concrete size, which is a size of is an array of 18 items. So people decided to transform this into a one-element array, and they even added a comment, like making explicit their intentions. So this was a fake flexible array transformation because they transformed it from 18 items to 1, right? And of course, well, that is a problem. That is something that we need to fix, because part of the change that introduced this bug is this code. And you can see here that tx packet is of the type of this fake flexible structure. The fake flexible structure is this QED LL2 tx packet. So in the middle of another structure, we have this fake flexible structure. So this is basically causing the same problem as the previous example. So this is going to cause undefined behavior, because at runtime, we are going to overrun the rest of the members in the structure. So we need to fix that. And how do we fix that? Well, the first thing that we need to do is to transform the one-element array into a proper C99 flexible array member, as you can see on the left. And well, it's actually on your right, right? Yeah, on your right. And on the left, you can see the other part of the change, which is, well, that declaration of an object of a type of a flexible structure should be moved to the end of the structure, right? So now with this, we fix the undefined behavior bug. So, well, this issue was a 3 years old bug. Okay, so then the last year I was presenting at Kernel Recipes. So before presenting, actually, I was reviewing my slides. So I was going through my slides, and just out of curiosity, I wanted to grab for this TXQ structure. So let's remember, the TXQ structure is the one highlighted in blue, and is the one that we just fixed, the one that contained the undefined behavior bug caused by declaring an object of a flexible structure just in the middle. So here in this case, we have tx packet is the flexible structure, and we are looking, I wanted to grab for txq. And well, what I found was this. And this is again the same problem. We again have another object after an object that ends in a flexible array member. So at runtime, if we allocate space for this flexible array member, chances are that we are going to write over CBS, the CBS object. So, well, that's the bug, of course. And this basically translates to the one to the part on the left. So we have highlighted in green the flexible array, and in yellow we have the flexible structure, and well, at the bottom we have the bug, right? That's the thing that we need to fix. That's the problem. We don't want to overrun CBS. So just out of curiosity, I wanted to see what that CBS object was, and it turns out that it's a structure full of function pointers. So yeah, that's problematic. That's a big problem. Okay, so the solution was, in this case, well, we just move, again, the declaration of that object from the middle to the bottom of the structure. And that would be the fix. So yeah, that was, I found this bug the last year, some months ago, actually. I guess it was in September. And yeah, in Paris, of course. And this bug fix was applied to multiple different stable trees. So we can see how flexible array members are having different ways of declaring flexible array members is problematic. And even when we declare those flexible arrays, as we should, we also need to be aware of how we are using those. Okay, so when I found this, of course, I sent the fix to the Linux hardening mailing list, and Case Cook replied with this. He was like, hey, nice find. So was this located with this other random compiler option? So how many of you know about this compiler option? Probably one of you know this. Paul, you know about this? You heard about it last year, actually. Okay. Okay, well, this is a compiler option that is currently under development. And the person that is developing this compiler option is Qin Xiao. Qin Xiao works for Oracle, and she's a great GCC developer. She's actually helping us to implement attributes and compiler options to harden the Linux kernel. And well, this is a part of the information in the patches. So yeah, basically this option helps us to detect those cases in which we have a flexible array member embedded or nested into multiple other structures. So we need to take a look to those pieces of code. And when I found this, I was helping Qin Xiao to test this compiler option, and I built my kernel with this option enabled. And well, I found almost 60K warnings in Linux Next in the last year. So that's a lot of warnings. And well, when I sorted them out, I realized that only 650 of those were unique. But anyways, I mean, those are a lot of warnings. So probably there are a lot of bugs there. So well, of course, when I fixed this issue the last year, I remember about this option, and I was like, okay, I need to go and take a look to my build logs and see if I found that issue at the time. Because at the moment when I realized that we had like a 60K warnings, I was like, oh my God, I probably need to do something else. Probably I'll come back to this like in a couple of years. So well, I went and take a look, and yeah, it turns out that this compiler option detected that bug at the time. So that means that it's a useful compiler option, and well, probably we should try to enable this option in coming months or coming years. Okay. Let's talk a little bit about the implications of flexible array transformations in the fortified version of main copy. This is a bit of the history behind the fortification of main copy. Okay, here we have a simple example of how we use main copy with a flexible array. Of course, we have here flexible structure with our flexible array at the end, and well, we want to copy some source of some size into the flexible array. So that's a quick sample. Okay, this is what you see there is a simplified version of main copy under config fortify source. So basically, main copy at the time was using this building object size function. What this compiler building function does is that we pass to this building function, we pass a pointer to an object, and we are going to get back the size of the object this pointer is pointing to. So that's how internally that version of main copy was working. So we get the size of the destination buffer and the size of the source buffer at compile time. And well, we can determine if we are going to run out of bounds. Again, this is the example of how we use main copy with a flexible array member. And well, when we use main copy, the fortified version of main copy with a flexible array member, it turns out that building object size was returning -1. And what -1 means is that this building function doesn't know exactly the size of this object. And that's actually expected because the size of the object is of incomplete type. So that was expected. Okay, but we wanted to see how about the other variable length objects, the other variants of declaring a variable length object, the ones that we call fake flexible arrays. Okay, what we saw at the time was that all of those variants for all of those building object size was returning -1. So even when we were using a one-element array, which is an object of a concrete size or of a zero-length array, this building function couldn't reason properly about the size of these objects. So that was strange. So yeah, it turns out that it cannot reason about the size of those objects. So now let's remember the case of sizeof. Sizeof returns different values for those objects. So in this case, sizeof is the one that is sane, right? However, all this can be a bit confusing because why is that the sizeof is returning, let's say, the correct values, but this building function is not able to do it? Okay, now we were curious enough to see what if we pass a pointer to any trailing array to this building object size function. So what happened was that it couldn't reason about the size of any trailing array. So it doesn't matter if we pass an object of a one-element array, of a zero-length array. It doesn't matter if we pass an object of 18 items or 100 items. This building function couldn't reason about the size for those objects. So that was a bit disquieting. So yeah, we wanted to know what was going on. So yeah, in this scenario, maincopy cannot sanity check any trailing array. So this is probably a case for go fix the compiler. So this is like a common expression in the kernel community. Together we go away sometimes. Yeah, so let's see if we can find out why exactly was the reason behind this behavior. It turns out that there are historical reasons for this. This is a piece of BSD code. Here we have sock address. Sock address, as you can see, it contains a trailing array of a concrete size of 14 items. And the issue with this structure is at runtime, this array could go up all the way to 255 bytes. So it was, at compile time, it was a structure containing an array of 14 items at the end, but at runtime, it behaves as a variable length object. So this actually is the reason why compiler people decided to just say, well, you know, if you are using a trailing array, we are going to assume that you're probably going to change your mind and that this code is going to behave differently at runtime. So we better don't lie to you and just say that we don't know about the size of this array. So yeah, this is part of the comments in this link. So you can see and take a look after when this presentation is available online. So okay, so what do we do about it? So in that case, we cannot sanity check any trailing array with a fortified version of maincopy. So what do we do about it? So we have two different problems in two different fronts. So on the kernel side, we need to remove the ambiguity of having different ways to declaring a variable length object. So we need to get rid of fake flexible arrays and transform them into flexible array members. And well, on the side of the compiler, well, we probably need to fix building object size. So when we remove the ambiguity from the kernel, now we are only going to left with C99 flexible array members as variable length objects. So whenever the compiler finds a one-element array or a zero-length array, it should be able to say, well, you know, this is by no means this is a variable length object. So here is the size, right? If it is a one-element array, well, you get the size of that one element. If it's a zero-length array, you get 0. And we could probably try to implement on the side of the compiler a new option, and in this case, fstrict-flex-arrays. So what happened is that this option was implemented. So this is already in GCC 13 and Clang 16. And let's see how this option works. So the default, by default, the level value 0 for this option, everything remains the same. All trailing arrays are going to be treated as variable length objects by the compiler. This is, if the compiler sees a trailing array of any size, it's going to say, well, you know, I have no idea the size of this object, so it is up to you what you do with that. So everything remains the same. With level value 1, well, with level value 1, only fake flexible arrays in C99 flexible array members are going to be treated as variable length objects. So the rest of the objects of other concrete size are going to gain bounce checking. So in this case, well, we are fixing the rest of the training arrays, except for the case of one element arrays and zero length arrays. With level value 2, well, we now fix the case for one element arrays. So only zero length arrays in C99 flexible array members are going to be treated as variable length objects by the compiler. So in this case, for those two different types of arrays, building object size is going to return -1. But well, at least we fixed the case of the one element array. However, we are left with the case of the zero length array, and we also would like to fix that, because we just want to use C99 flexible array members as variable length objects. So what do we do about it? Well, probably the next logical step is to implement level value 3, right? But Clang developers had an issue with that. So what happens is that in Clang, we have this compiler option, and what zero length array does is that it's going to tell you, it's going to yell when you declare a zero length array. So Clang developers were like, well, why do you need a level value 3 if you just go and enable this compiler option? That's it, right? Just don't use zero length arrays. The issue with that is that this option spits like thousands of warnings. And the reason for that is that zero length arrays are not only used in the kernel as variable length objects. People also use them as markers in structures. So this is an example. Here we have struct marked. And struct marked, it contains a couple of members, header start and header end. And the reason for that is because developers are defining an area. Yeah, a question? We are going to get into that. So the next slide. Okay, so so yeah, this is one of the ways kernel developers use zero length arrays. So you can see at the bottom, and copy is copying just data into that section, right? Marked by those zero length arrays. However, we can use a struct group. So we have a helper in the kernel that allows for having these members together into a name structure. So in this case, we can use that helper. We can avoid using those zero length arrays as markers, and we can use main copy, as you can see at the bottom, just applying size of to p in the new name for the struct group, which in this case is header, HDR. So now you can access all the members either directly or through this new name for the group structure, which is HDR. And well, another thing with zero length arrays is that sometimes under certain configurations, we are going to end up with arrays of size 0. So under certain configurations, probably the array is going to be, the size of the array is going to be greater, but probably under other particular configurations, well, we are not actually going to use that array, so that the value for that array is going to be 0. So yeah, the thing is that zero length arrays are here to stay in the kernel, just we don't want to use them as variable length objects. So fortunately, that issue was resolved, and Clang developers agreed to implement this level option. And well, we now have this level value 3, and this will allow us to only use C99 flexible array members as variable length objects. So if people use a one element array, well, building object size is going to return the value of that one element. If they use a zero length array, this building function is going to return 0. And just in the case of a C99 flexible array member, this building function is going to say, well, I still don't know what the size of this object is, because, well, I just don't know. And yeah, well, with this, we gain bounce checking on all the rest of the fixed size trailing arrays. So yeah, that's what we needed. Okay, so this compiler option was enabled in Linux 6.5, so that was great. These benefits use UV sandbounds and fortified source. And well, now in the kernel, only C99 flexible array members are considered variable length objects, and that is great. So yeah, we've gained bounds checking on trailing arrays of fixed size, right? However, we are still left with the case of the flexible array members. So what do we do about it? Well, for that, probably we need a new attribute, and probably a counted by attribute. Usually, when people use flexible structures, apart from the flexible array member, they also include another member which is going to hold the total elements at runtime for that array. So in this example, we have elements. The elements variable is going to contain that number of elements for our array. And if we had a new attribute and we could apply this attribute to elements, that would give the compiler enough context to reason about the size of this array at runtime. So this attribute is coming in GCC 14, is under development. Kim Xiao is working on that. However, in the meantime, in the kernel, we had already paved the way for the adoption of this attribute. So we already have these macros in the kernel. So we've been doing the work of applying this attribute to all the flexible structures that we could possibly do.
On the fly, it will run FStream once a
another
week.
great news is that
Like
this attribute was just released in Clang 18. So this is already in the wild. And this is how this works. So this is part of the release notes. So yeah, the counted by attribute is C only. It's only for the C language. And well, it is going to be applied to that variable that contains the total number of elements for our array at runtime. And well, this also benefits another 10 minutes. Oh, wow. Okay. Well, this benefits another building function, in this case, building dynamic object size. Okay. So let's see. A quick recap. Flexible array members are mostly done in the kernel. I started doing this work in the Kernel Self-Protection Project in 2019. In Case Cook, this year fixed probably the last remaining of these issues. Strict-flex-arrays is enabled. So with that, we gain bounds checking of fixed size arrays. The counted by attribute is released in GCC and is coming soon is released in Clang and is coming soon in GCC. So with this other building function gains insight into the size of those objects, those flexible array members at runtime. So the next sensible thing to do is, well, we need to replace building object size with building dynamic object size. So that's what we did. And now main copy is, instead of using building object size, is using building dynamic object size. So with that, we gain visibility into the size of flexible array members at runtime. So that's greater fortification for the kernel. Okay, quickly, let's see how we were doing these transformations or fixing these problems in UAPI. UAPI is always problematic because, well, we cannot break user space, right, on purpose. Okay, so this is an example of how we were doing those transformations. We cannot just merely remove the one from the declaration, because we would alter the size of the structure. So in this case, what we were doing we were duplicating the whole thing and just adding a flexible array member so that the flexible array member could be used in the kernel space and the one element array could still be used in user space. Okay, for that we had a declare flex array helper because it happens that flexible array members could not be declared in unions or alone in structures. So that was an issue. So we come up with this helper with Dawson macro magic thing and preprocessor magic thing. And well, yeah, the bad news is that the size of the structure will remain the same. It's not going to be altered. Okay, soon declare flex array won't be needed anymore because in Clang 19, a new implementation is going to be released and it's going to make possible to use to declare flexible array members in unions and alone in structures without any preprocessor magic. So that's a great thing. Okay, so quickly, flexible array members, flex array member node at the end. This is currently under development. So this is the issue that we had, right? we have a flexible structure, and in the middle of another structure, we have an object of this type of structure. So that is causing troubles. That's suspicious code that we need to take a look at. And let's remember that we had 60K of these warnings. Okay, so I'm currently doing this work. Those patches, I already landed a lot of patches in Linux Next. So I saw multiple different cases. One of them is when the flexible array members are not actually being used. So in this case, we can just remove the flexible array member, and with that, we fix hundreds of those issues. Well, actually, this fixes 100 of those warnings, right? Well, on other cases, when the flexible array member is never accessed, and only the rest of the members are being used. Usually, people find convenient to use a flexible structure in the middle of any other structure because they want to use the members, the rest of the members, not the flexible array, because they are sort of like implementing a header, right? Okay, I have 5 minutes, great. Okay, so in that case, we could use, one strategy could be to have two separate structures, one which is the original, flex-struct will be the original, the one that contains the flexible array member, and the other one would be the one that will contain the rest of the members, right? So the original without the flexible array. However, this creates some problems because if we need to update the original structure, we will need to update the code in 2 different places. So that's twice problematic and that's error prone. So for that, we could use struct-group. With struct-group, what we can do is just add a new tag structure into the original structure and use that new tag name as to declare another object within another structure and leaving out of the equation the flexible array member. So this is an example of that. And this is a fix that I sent to Linux Next. This is how it works. As you can see, we are grouping the members of the structure within, in this case, a new tag structure, and the flexible array member, we are not touching it. And we can declare now an object of the type of the tag structure. And with that, we leave out of the equation the flexible array member, so the compiler will lose visibility into that flexible array member. So it won't warn about it. However, sometimes people are using implicit unions with flexible array members and other arrays of concrete size. So here we have an example. At the bottom, well, the part on the left, the code on the left, we can see an implicit structure. What is an implicit flexible array, a fixed size array? An implicit union. Well, we have a flexible structure, and just immediately following it, we have an array of a concrete size, which is of the type of the same type of the flexible array member, right? So what happens is that basically the flexible array member and the concrete size array share the same address, right? That's a trick that people like to use, because sometimes it happens that they know how big the array is going to be at runtime, so they don't need to allocate any extra space, they don't need to do any other sort of special computation for that. They just allocate a space for this structure that contains the implicit union, and that's it, right? They can now point to the flexible array member, and they have enough space to move within the flexible array member. Sometimes for that, we need to use another trick. In this case, we need to use container-of. What container-of does is that we are going to get a pointer to the flexible structure, and when we get a pointer to the flexible structure, we are going to be able to access the flexible array member that we left out of the equation at compile time. So that's a nice trick, in my opinion. Probably I like it because that's what I'm doing, right? But anyways, here's an example of that, how we use that. So in this case, max digest data is the structure that contains the implicit union. And through container-of, we are getting a pointer. I would like to use a pointer here, probably. Oh, you cannot see it. Okay, anyways, yeah. Through container-of, we are getting a pointer to that flexible structure, and once we get a pointer to that flexible structure, well, we can just now directly access diets, the flexible array member diets. So the code at the bottom, the main copy code at the bottom, is accessing digest as a flexible array member, not as a variable length object. Not this digest. Not the digest of a concrete size. Okay, and well, another case would be the same as case 3, but on stack. For that, we use declare flex and declare raw flex helpers. That's a topic for another conversation. However, you can see some examples here in the when you have access to the presentation. And well, currently, I have sent a bunch of patches to Linux Next, and I managed to go from 650 to less than 400 warnings with this strategy. And well, conclusions. Well, flexible array, strict flex arrays is enabled. Counted by attribute is a reality. We are using now building object size, and with that, we are increasing considerably the coverage of bounce checking. So we are basically gaining bounce checking on flexible array members. And well, fortified source and UV sound is benefits from this. A lot of the vulnerabilities of the recent years could have been prevented with the recent fortified version of main copy. And well, we are fixing bugs in user space too, and also, of course, in kernel space. And now we have a clear vision of how we are going to fix and finally enable the flex arrays member not at the end option in the kernel. And well, the security of the kernel is being significantly improved. And with that, thank you.